I'm taking a lot of metformin and NMN and Elysium, and that's pretty much it. I mean, I take like Lipitor, and I do like 5 days a week of 16-hour fasts. And I'm looking for the right kind of supplement.
Bob Nelson is 57 years old. He lives in San Francisco, and for the last few years, he's followed a rigorous routine of drugs, supplements, and lifestyle habits like fasting designed to alter his body chemistry. Bob isn't sick, but he has a specific goal in mind with these measures. He's conducting an N of 1 experiment on himself in an attempt to slow down the process of aging.
I generally kind of have a fear of death, which is part of, what motivates me to be interested in longevity. So it's like, it is a selfish thing. And I have no idea whether it works. I don't feel my age.
Bob is a biotech investor, so his job is to spot trends in health and technology to build companies he thinks will make breakthrough transformative science. It's through that work that Bob was exposed to an array of relatively recent biochemical discoveries in aging research, which are for the first time starting to expose the molecular mechanisms that underpin the aging process and open the door for treatments that could potentially prevent or reverse those changes. At the same time, a handful of existing drugs have serendipitously been observed to slow aging, leading to a new wave of interest in longevity. And Bob is far from the only person to become captivated by the idea of staving off the decline of age. In this episode of Stereochemistry, we'll hear from some of the scientists who are teasing out the biochemical secrets of aging. We'll look at the drugs that are in development right now to tackle aging at the molecular level, and we'll find out what we know, and don't know, about this biological process that affects all of us. I'm your host, Kerri Jansen. For this episode, I've asked C&EN reporter Laura House to join us. Laura is based in Heidelberg, Germany, and covers chemical biology. Thanks for joining us, Laura.
Hi, Kerri.
So, Laura, it wasn't until we started working on this episode that I realized I don't really have a great sense of what it means to age. I mean, we think of getting older, the passage of time, but scientifically, what is aging?
That is a great question, Kerri, and one I asked a lot of different people in recent months. And you know what? There are a lot of different ways of thinking about aging. But we all know what it can look like. Over time, you have less energy and less strength or vigour. At the same time, smell, taste, eyesight, hair, and muscle tone, all of it starts to just change a little bit as your biochemistry changes.
And those biochemical processes are at the root of what we're talking about today. Can you give us an overview? What does aging mean at the molecular level?
Well, there are a lot of things going on. For one, there's low-grade chronic inflammation. Inflammation is switched on as part of a healthy immune system to coordinate fighting infections and repairing damage. But as we age, chronic inflammation can start hammering our cells and tissues, causing damage. And then there's also a whole host of processes happening inside cells. There are chemical changes to DNA that alter how the cells keep working. Proteins misfold and clump together, which stops them working properly, and the mitochondria in the cell don't work properly, which changes metabolism. And different types of cells can change. Stem cells stop being able to create new healthy cells, and you can also start accumulating a particular type of cell that can cause damage. Those are called senescent cells. Senescent just means old. These senescent cells are going to come up a lot in this episode. They're a key target for many of the treatments being developed.
So if we're talking about disruption and damage inside the body, is aging a disease?
No. Everyone I spoke to for this podcast was pretty clear about that. For one thing, there's enough ageism in the world without othering older people even more. But also, researchers don't think that everything about aging is bad. Instead, as scientists understand more about the different ways our biology changes as we age, they can also see how those fundamental aging processes can contribute to disease. I talked with James Kirkland, a gerontologist at the Mayo Clinic, who also researches how aging can affect diseases. He told me aging is actually the number one risk factor in disease.
For example, 80% of the risk of getting Alzheimer's disease can be predicted from knowing a person's chronological age alone. The relative risk of having a heart attack is increased 2 to 4-fold by having a high blood pressure, high blood sugar, high cholesterol, positive family history. But it's increased by over 100-fold if you're 85 as opposed to 35. So if you put aging as a risk factor, for any of the major chronic diseases. And if you draw histograms, bar graphs, and you put aging as a risk factor, you don't even see the other risk factors.
And we've seen that with COVID-19 as well. Older people are more likely to get severely sick when infected because their immune system is weaker than younger people.
Right, and their immune system is weaker in part because of that build-up in senescent immune cells and amped up inflammation. So this gets at a key aspect of anti-aging research. The biochemical processes of aging make other diseases worse. So for many researchers, slowing the progression of aging isn't about being able to live forever. It's about making the life we have healthier, increasing health span, not lifespan. Here's Bob Nelson again.
I don't really want to just live a long time without having, truly a increase in health span. So I like this idea of, being like the little thin little old lady 100-year-old that you see whose like mind is, sharp and, everything's kind of working just fine. And that seems to be an okay state to me.
So at the beginning of this episode, we heard Bob list a whole bunch of drugs he's taking in an effort to extend his health span. Where's the science at on those?
Right. He mentioned Lipitor, which reduces cholesterol, and NMN, that's nicotinamide mononucleotide, which is a supplement that in mice has been shown to boost metabolism, and Elysium, a dietary supplement that's advertised to improve cellular aging. He's also taking metformin. That's a drug that's commonly used as a diabetes treatment, but has recently been getting a lot of attention in the aging research community. We'll talk more about that in a moment. And then there are two other main types of drugs aging researchers are interested in. One type is senolytics, which help rid the body of senescent cells that accumulate as we age. Another class of drugs are called rapalogs. Rapalogs target a specific series of biochemical reactions that are involved in aging. Rapamycin was the first of these to be discovered. Rapalogs are similar compounds that have since been designed to do the same thing. But to be clear, we're not advocating you take any of these. We don't yet know what the negative impacts could be for taking them for aging, and any changes you do want to make to your lifestyle should only be in consultation with a doctor.
That's important, so let's hear it one more time.
We're not advocating you take any of these.
Got it? Okay, let's move on.
As researchers have come to understand more about how aging works, they've now got to the stage where some are setting up trials to see whether different drugs can improve how we age. So we're going to talk to some of the researchers involved in these trials, as well as academic researchers who think there's a lot more to be uncovered about how aging works in our body.
If they're aliens and they will come here, they'll be shocked to see older people. They would say, you didn't deal with that?
That's Nir Barzilai, director of the Institute for Aging Research at the Albert Einstein College of Medicine.
If they came farther than Mars, right, they solved aging.
I don't think Nir does actually expect us to be visited by aliens, but it's interesting to consider that we don't necessarily have to accept aging in its current form. Nir also noted that the health issues traditionally linked with aging are not limited to folks with an advanced chronological age.
It's not about the older adults only. People who are treated for cancers with chemotherapy and radiation that, by the way, are inducing aging quite effectively, they are getting older, in particular young people. They're getting older. Young people after therapy get second cancers too, but they get a heart disease and hypertension. They get other diseases. People who have HIV have age-related disease 10 years earlier than other people.
Nir has several interests and ideas for how to treat aging-related health issues, and one of the drugs he's very interested in is metformin.
Right, you said that drug has been really popular lately in aging research. So why is that?
Well, that drug has actually been around for more than 60 years as a treatment for type 2 diabetes. It's a small molecule, and in people with diabetes, it decreases glucose production in the liver. But in 2014, a group of researchers at Cardiff University in Wales found that people with type 2 diabetes who were taking metformin live longer, on average, than people without diabetes who didn't take the drug. That caught the interest of a lot of researchers, including Nir. He's especially interested in metformin because of its long track record of use. Millions of people have used it safely for many years.
There are billions years of use, and we know everything we need to know about metformin. It has a spectacular safety record. Its major side effects is that you live longer.
The safety record of metformin is why Nir says he's opted to trial that drug over senolytics and rapamycin, as well as the fact that it's very cheap in comparison. But he expects that all the drugs we discuss, and other treatments, might end up being used in combinations. One thing you realise as you learn more about this field is that it's not enough to simply say that one drug affects one protein, which then affects a single chain of reactions. Instead, it's more like an interconnected web. Each drug might affect one section of the web more than others, but they can all have effects, and that's another big plus in Nir's book.
I believe that we have to look at all the hallmarks to develop drugs for all the hallmarks of aging. The effect of drug like metformin on health span, we predict it's going to give you 2 years, additional 2 years of health.
So that's a big claim, but what does the data say? Is metformin living up to the hype on aging?
Well, some doctors will already prescribe it off-label even if you're not diabetic. That's how Bob got hold of his. But there hasn't yet been a clinical trial to show that it slows aging. Nir is trying to start up a trial to see if metformin can live up to the hype. The trial is called TAME, T-A-M-E, Targeting Aging with Metformin. It's currently paused because of the pandemic, but I find the trial design itself really interesting. Instead of looking at whether the drug affects a specific disease, they're just going to look and see if metformin makes a difference to a whole range of age-related diseases. Nir plans to give metformin to over 3,000 people and monitor them over 6 years to see if the onset of various diseases like stroke or heart failure can be delayed.
Our approach is, look, we're saying that we're going to delay aging and we're going to delay diseases. We are totally agnostic to which disease we have to target, okay? We don't care what disease you have, and we don't care what disease you're going to have, whatever it is.
Okay, so scientists are testing whether metformin improves health span a little in a general sense. What about those other treatments you mentioned?
Right, so senolytics and rapalogs. Let's start with senolytics. Those caught the attention of aging researchers around 2013, and they kill senescent cells.
Let's talk a little bit more about senescent cells. You said that they're a type of cell that accumulates as we age. How does that end up causing problems in our bodies?
Okay, if you think back to biology class, you might have seen videos of cells dividing. Well, senescent cells are cells that stop dividing, but also don't die. And mostly these cells are useful. They help stop cancers, they're involved in wound healing and fetal development, but at some point as we age, these senescent cells collect up and start causing problems, secreting chemicals that cause inflammation, things like cytokines, chemokines, and proteases. Here's gerontologist James Kirkland again.
What we're trying to do is get rid of senescent cells that have outstayed their welcome, where they've started to dampen down the immune system, which normally clears them, and where they've gone beyond what we call a threshold effect, where their rate of formation exceeds the ability of the immune system to clear them.
Got it. So how do senolytics work to get rid of senescent cells?
Ooh, sneakily. A bit like some cancers, senolytic cells are very resistant to dying. Instead, they live on, damaged and giving out a toxic mix of proteins and other compounds that cause neighbouring cells to die. You can think of them as zombie cells.
Okay.
If these zombie senescent cells aren't kept in check, they can slowly cause more and more damage. James and his lab wondered how these senescent cells could survive when they were kicking out cell-killing poisons. They found that senescent cells have internal defences to protect themselves from these toxic compounds. If you knock out these defences, the cells will die. In 2013, the researchers discovered that 2 existing drugs, one is a cancer treatment and the other a supplement, could kill these zombie cells by targeting these newly identified pathways. And since then, more defences and more senolytic compounds have been discovered.
Well, we're working as fast as we can. It has been quick. We only discovered the drugs in May 2013 and published them in early 2015. And already, there are multiple clinical trials going on.
But there's no telling whether they will work. It's worth remembering that no drug has been shown to be safe and effective for aging. Unlike the metformin study, the trials James is running are trying to see if senolytics can reduce specific markers of aging in people who are very sick with aging-related diseases. But instead of taking a daily pill, like metformin, volunteers in the study get a short course of these 2 drugs or a different senolytic. A short, sharp shock that's meant to clear out the senescent cells and then reset the amount in the body to more youthful levels.
We're interested in a hit-and-run approach, much like is used for treating certain kinds of infections. We sort of viewed senescent cells like a bad bug, like bacteria that we wanted to get rid of.
Keep in mind, although some pilot trials with senolytics suggest they work, there's a long way to go before those drugs might be prescribed. That's the same for the class of treatments called rapalogs. These are the third kind of drug that people think could help extend health span. The hope is that rapalogs could reverse some of the effects of inflammation. The term rapalog, by the way, is a shortened form of rapamycin analog, because those drugs are related to the compound rapamycin.
Right. Rapamycin is a compound produced by bacteria that has turned out to have a lot of medicinal properties. Our colleague Beth Helford did a deep dive on that compound a few years ago.
Yeah, rapamycin has been touted as an anti-cancer drug because it stops cancer cells dividing, and researchers have found that it also inhibits a series of reactions started by a protein that scientists named mTOR, which stands for Mechanistic Target of Rapamycin. What's interesting about rapamycin and mTOR is that mTOR has been shown to act like a control system for coordinating how cells manage their nutrients, which is something we know gets out of whack when people get older. Then, in 2009, researchers found that in mice, rapamycin could extend the lifespan by about 9 to 14%. James Kirkland again.
Drugs related to rapamycin, there are many of them. Many of them are used now as immunosuppressants to prevent graft versus host disease after transplantation. They act on senescent cells to prevent senescent cells from producing a lot of pro-inflammatory factors.
So there are senolytics that can get rid of excess senescent cells, and rapalogs that can tamp down the inflammatory compounds senescent cells give out, and also prevent new senescent cells from being formed.
Yeah, and James told me metformin, the other drug we've discussed, can also reverse some of the damage caused by senescent cells. Both he and Nir think all these treatment options might be needed, as well as some other new approaches. Remember, the treatments we've just discussed are all based on drugs that were developed to target things other than aging. They just happen to affect the markers of aging too. The next phase is for researchers to develop drugs specifically for aging-related problems, and that's a really exciting field right now. There's a lot of work still to be done.
We're going to take a quick break. When we come back, we'll hear about the next generation of aging treatments and how researchers are working to turn serendipity into science. Hey everyone, it's me again, Kerri Jansen, your stereochemistry host and producer. We've been making stereochemistry for 3 years now. And first of all, I want to say thanks to all of you who tune in every month, subscribe and rate the show, and engage with us on social media. It's because of you that we're able to bring you stories about cutting-edge research, chemistry culture, conversations with Nobel laureates, and more. And we're so excited to keep sharing these stories from the world of chemistry. And now we want to hear from you. We are conducting a survey of podcast listeners to help us decide the future path of stereochemistry. We want to know what you like, what you don't like, and what you want to hear more of. So if you'd like to help us shape the future of stereochemistry, here's what you do. Go to the link bit.ly/stereochemsurvey. Fill in as many answers as you like and hit submit. You'll be entered for a chance to win a $25 Visa e-gift card. Once again, that survey link is bit.ly/stereochemsurvey. We'll put that link in this episode's show notes as well. Thanks again for listening. And now, back to the show. So Laura, we've just heard about 3 classes of potential anti-aging treatments based on existing drugs. And you said that some researchers are now exploring a more targeted approach. Tell us about that.
Yeah, this is something we've started to see pretty recently. Researchers drilling down into the specific biochemical processes of aging to develop new drugs to target them. It's only in the last 10 years or so that we've begun to understand the specific molecular mechanisms that underpin aging.
And we've already heard that the process of aging is really complex. So what was the breakthrough that enabled scientists to start to figure this out?
Well, actually, it has to do with diet. Remember at the beginning of the episode, Bob says he fasts several times a week in addition to taking all those drugs? And he's not the only one who does. Now, the scientists I spoke with noted that the jury's still out on whether that can slow aging in humans. And again, if you're considering making any kind of big change to your diet, talk to your doctor first. But calorie restriction, or CR, has been a key part of aging research for a long time. It means exactly what it sounds like, limiting calorie intake either through smaller meals or reducing the frequency of meals. In animal studies, it's generated some pretty interesting results.
And I thought, how is it possible that something so simple could, influence something so complex?
That's Ros Anderson, who studies aging and diet at the University of Wisconsin.
And I got hooked on the biology. So for me, it was never really about, living longer or anyone else living longer for that matter. It was just the straight up biology. Look at it this way. It's amazing. It works in a yeast, in a fly, in a worm, in a mouse, in a rat, in a dog, in a monkey. It seems to be a very, very fundamental process that caloric restriction is kind of catching a hold of.
Ros first got hooked on the basic biology of aging during her postdoc. She has found that in many animals, calorie restriction can have a dramatic effect on how well and how long the animals live for.
This is where something like CR becomes like super cool, because we know we've changed the pace of aging in the CR animals. We know they live longer. We know they have less disease, and what disease they have progresses more gradually.
Wow. Do scientists know how exactly calorie restriction is having this effect?
We don't entirely know, but researchers like Ros know it changes the metabolism and signalling reactions in our body, including some of the pathways that are influenced by the drugs like metformin and rapamycin that we discussed earlier. Ros is one of the researchers trying to figure out more about how fasting helps change aging. The potential she sees is not necessarily about proving the value of a new fad diet. Rather, it's a way to uncover the key biochemical processes involved in health and aging.
Fasting mimicking diet, time-restricted feeding, every other day fasting, all of these paradigms, they show terrific promise if you're a mouse. But I think we will be able to tease out what the beneficial components are.
For example, if you trace back the development of senolytics, you find that people became interested in senescent cells because mice on restricted diets were found to live longer and have fewer senescent cells. Ros is mostly interested in using the biological changes induced by calorie restriction to puzzle out the biology behind aging and how it works. Other researchers are using genetically modified animals to probe those biological changes. And most recently, researchers are also starting to use large-scale laboratory analysis and AI to try and build up a descriptive picture of how we age and how that varies from person to person.
And what do you mean by that?
Well, think of it this way. I'm about to turn 38. But we've been talking about how, in the future, I could slow down or reverse some of the biological processes associated with aging. So the dream is to measure a bunch of different markers and then be able to separate biological age from chronological age. Then, scientists might be able to advise an individual how to change or improve their health based on their specific aging profile. That individual-focused approach will be a big change from how aging research has historically been done. At Stanford University, Mike Snyder has been working on this for several years.
So traditionally, the way people have followed aging is they'll measure a bunch of old people and a bunch of young people. And they'll say, well, these are the markers in old people, and these are the ones in young people. And a good example is hemoglobin A1C.
Hemoglobin A1C is an oxygen transport compound in blood that is chemically linked to a sugar and is used to monitor people with diabetes or pre-diabetes.
We know that goes up with age. When we say, okay, these are markers of aging, and they're valid, it's true. But what's very interesting is we don't really know how they work at the individual level. And that's where we come in, because we've been profiling people while they're healthy, but we can see how they're aging over time, what's going on. And what we discovered is there's about 600 molecules that do change in people over time, but they don't all change the same in all people.
Of course, an individualized approach to studying aging will generate a massive amount of data. Mike actually started this study by monitoring his own health, and to date he says he has about 2 petabytes of data relating to him, and a petabyte is 1,000,000 gigabytes. He also has another 2 petabytes that cover the participants in his research study. And that's where computational algorithms come in to process that data. Scientists hope to use AI to identify how individuals are aging and what changes they can make to their lifestyles to slow that down. Bob Nelson is convinced that's going to be a key growth area in the next few years as machine learning and an understanding of key pathways to measure both improve. That could put this research and the treatments it may yield on the fast track.
And I do think it will transform healthcare as we know it in the next, 10 or 20 years for sure. You can think of aging-related diseases as really the most expensive, the most impactful and the deadliest things that we deal with. I mean, I'm interested in longevity because it applies to me, right? And I am interested in it as a societal problem, and I love the idea of preventing disease. But like, it has occurred to me that I would like to live a long time. And so I'm not pretending that it's some egalitarian act. And the only thing that I'm interested in is that, that I hope it prevents disease in everyone else. Like, I'm pretty interested in preventing disease in me too.
And as more investors like Bob get behind aging-related projects, scientists are expecting an explosion of new discoveries. NEAR is one of them.
So we're catching a wave. I would describe the wave as it's going slowly, but it's going to be quite big when it gets to its peak. And I think that the next few years will be remarkable in what we can do and what we can show to everyone.
So what about you, Laura? Are you itching to get your hands on these treatments?
Well, I'm not about to start taking a lot of the drugs that we've discussed in this podcast. And again, we're not advising any listeners to do that either. We don't yet know what all the downsides might be. But I am interested in following the data, and I'd be lying if I said that the promise of extending my health didn't appeal. The idea that Bob mentioned at the beginning of the show, of being a sharp old granny who's still living independently, sounds pretty good. It'd be even better if my knees and my internal organs were all still working into my 90s.
But do you think that's possible in our lifetimes?
Actually, I'm more positive about that future than I was when I started talking to people about their work studying aging. And one reason is that several of the researchers told me that it's looking increasingly likely that many processes in aging are very tightly interlinked. You remember how early in the episode we talked about how we can think of the biochemistry of aging as kind of like a big web? James told me that the evidence is growing that targeting one of these biochemical processes of aging might actually help with all of them. It's what he calls the unitary theory of fundamental aging processes.
It's still a theory, but it's looking increasingly like all of these processes are very tightly interlinked, such that if you intervene in one, you tend to affect all the rest. In fact, we haven't found exceptions to that so far.
And so even though aging is very complex biochemically, it's also so interlinked it might not need a different drug for each set of reactions or pathways, just a few tuned to your immediate needs. And that might mean that the idea will change of what aging is biologically to be a more granular understanding that researchers like Roz and Mike are building. I think for now, I'm just going to try to eat healthily, exercise, and socialise with friends, as much as the current pandemic allows. Everyone I spoke to could agree that those were good ideas. But perhaps aging research will help us understand how to be even healthier into our old age.
I'm very tired of prescribing better wheelchairs, walkers, and incontinence devices. And all of us, I think every geriatrician, wants to get something more fundamental out there, whether it's going to be senolytics or some other intervention. I hope something comes along.
This episode of Stereochemistry was written by Laura Howes and produced by me, Kerri Jansen. Story editing by Lisa Jarvis and Amanda Yarnell. Production assistance by Gina Vitale. The music in this episode was Paradise Drive by Charlie Ryan and Bounce by Seth Parson.
Stereochemistry is the official podcast of Chemical and Engineering News, which is published by the American Chemical Society. Thanks for listening.